Okay, now we'll continue on with section 2. So we're on example 4. And suppose we had the number of outcomes. We want to find the number of outcomes for each of the following. And suppose a county license tag has a 4-digit number for identification. If any digit can occupy any of the 4 positions, how many county license tags could we have? So I like to think of having these slots again. And we know that any of the 4 digits 0 through 9, which is 10 digits, can be in this position. Any can be in this, or this, or this. And so with the multiplication counting principle, that would tell us that we would have 10 to the 4th power, or 10,000 different license tags that we could have. Now, I'm going to put a little bit more parameters on this. And so now if we have a county license tag but we don't allow duplicate digits, how many different county license tags could we have? Well, if we're not going to allow those digits to repeat, we aren't going to have 10 opportunities to place a number in that spot. So we'll only have 9 different ways to put a value in the second slot, and then 8 because we would have already used up 2, and 7, and so on. So we significantly lower, almost cut in half, what the number of license tags we have based on that. And then lastly, let's suppose that we have up to 4 digits. How many different license tags can we have in that case? And we're going to allow the repeats. So we could have a 4-digit case, but it could be we could have something just like that, just a 1-digit license plate, or maybe a 2-digit license plate, or maybe a 3-digit license plate. So we have to take all those cases into account. And so we could have 10 1-digit license plates. We could have 10 times 10, or 100 2-digit license plates, and so on. Now, it's real careful. You need to be careful about the wording of an and versus an or. We want a 1-digit case, or a 2-digit case, or a 3-digit case, or a 4-digit case. And when we use that word or, we would want to unite those and add those together. So or will generally mean that you're going to be adding something. Now, we have some different probability rules that you're familiar with. You know that a probability of an event is not just any old number. It's going to talk about, in a long series of repetitions, what the likelihood of something happening is. So it's not just any old number from 0 to 1, but it will have to be a number that is something from 0 to 1. It can't be negative. It can't be bigger than 1. But don't think it's just any old number. It's going to be a probability is going to talk about, after a long series of repetitions, what would happen, how often that value or that occurrence or that outcome would take place. Now, the probability of the entire sample space, if we list every element down in the sample space, the probability that a sample space will happen will always be 1. We had the term complement before in FS and in other probability classes. But we'll use a little bit different notation here. If we're talking about the complement of an event, we will use, in your textbook, the kind of to a C power. Here's a picture down here of a Venn diagram that's showing the complementary pattern. So if this box was representing my entire sample space, event A does have a complement. Its complement is not A, and so A to the C power. And those two are said to be mutually exclusive or disjoint, but they will exhaust the sample space when you take the two together. So they are not going to, can't happen at the same time. They have nothing in common. However, they will also use up everything in the sample space. There isn't anything that's not either this or that, and nothing can be both. Now, another term is a disjoint event. If I have two events, A and B, here's a nice, again, Venn diagram of the situation. Disjoint events are events that cannot happen at the same time. Once again, these two events are disjoint, but just because two events are disjoint does not mean that they have to be complementary or use up everything, but they can't cross or intersect. And that would be the notation here, that I would, if I want the union of two or want to unite two sets together and find the probability that this event happens or this event happens, it will be as easy as just finding these two probabilities and adding them together. Now, we also worked in FS on the idea of independence. And independence, when I have A and B are being independent events, we know that the two events would be independent if the occurrence of one will have no impact on the occurrence of the other, and vice versa. So if A and B don't have anything to do with altering the probability of the other, then we would say that they're independent. And this is what will happen if you have two events that are independent. If you actually count or figure out what the intersection of two events are together and find the probability of each of their probabilities separately, the product of these two will equal the intersection. And we'll do more with this in this next example. So let's skip down to number 5. So on number 5, we have the government data would show that in 1 year that 27% of the civilian labor force would have at least a 4-year college education, and that 16% of the labor force work as laborers or operators of machines or vehicles. So the question is, can we conclude that the intersection is going to be just the product of these two probabilities for our situation? So if we have this, I'll call this event A, that 27% have this characteristic, and if 16% have this characteristic, can we automatically just find the intersection by multiplying the two together? In other words, can I just find this intersection by just multiplying these two probabilities together? And we're going to find out we cannot do that. We don't necessarily know that the two events are independent. If having a 4-year education or more has some impact on whether you'll be a laborer or an operator of equipment, then the probability of their intersection will not just be the probability of the product of these two. So, and in fact, we probably could collect data and actually find that they are not going to be independent events, that if you know you have this type of an education level, you are probably less likely to end up being in this type of a job. It's not going to be as a solid rule by any means, but oftentimes people will go to college or have an education so that they don't have to work with more of a manual labor. All right. Next page. This will be the last page that we will do for this section. This goes back with the independence idea again. So you can look in your book on page 216 to see this data. But this was a question, again, out of your book. And from this table, you can see that we have some categories of the level of education and the age of a person, and trying to find out if there's some relationship between the education level of people and the age group of people. Or basically, is there no difference between people of different age groups and whether or not they've completed 4 years of college or not? So you have a lot of data that's listed in the table, and you should be able to verify that this would be the probability of randomly choosing a person from the data given on that table and finding out whether the person had completed 4 years of college. The table total, and these are the total people that had the 4 years of college. Likewise, we're finding what's the likelihood if you randomly chose a person that the person would be in the age category of 55 or older. Again, the table total, and then looking at the part of the table that has that characteristic of 55 or older. Now, when we find the intersection, you should look at the table and see that we would want all the people that have both characteristics in the table. And when we look at that in the table, we'll find out that there are 8,005 people in that category out of the table total. Now we can actually do a test now to determine whether A and B are independent. If we multiply these two probabilities together, we find out that we get about 7%. In reality, the intersection is only about 5%. So if we had independence, this product would actually be the same as the actual probability of the intersection. This is not the probability of the intersection. This is what came from the actual table. And so we can see that A and B are not independent events. So we would have expected there to be, if there was independence, we would have expected to see the characteristics happen together about 7% of the time, when in fact it only happened about 5% of the time. So these events are dependent events. And now it's time for you to do some practice.